Hello everybody, my name is Kuneh Shah. I'm going to be focusing on the topic of field-oriented control in PMSM motors. This is PHN 313 Signals and Systems video PPT. My enrollment number is 22123040. So let's start by the introduction. I know signals and systems is a big topic, but I thought of focusing on field-oriented control for motors because of my interest in motors as well as some uh, discussions in the lectures regarding motors and fans and systems in general. So my focus in particularly in FOC would be in Clark and Park transforms. I am part of the IIT Roorkee Motorsports as an e-powertrain engineer, and I am involved in the motor control systems in electric powertrains. As you can see, this is our car. Here somewhere in the below the driver there is a motor which is then connected to the drivetrain. So yeah, this is me. Moving forward, what are the steps of motor control? So let's start with the three-phase inverter. Uh, as we can see, there are 6 MOSFETs which are used in as switches to either get connected to VCC or ground. There are 6 in total combinations which can be shown. As you can see, there are 6 combinations wherein some will be on, some will be off, which would result in only a particular number of arrows out of the 6 you can see to be on, and leading to a circular motion in the stator magnetic field, which would then translate into the rotor magnetic field along with some slip. So the problem with this inverter is that it does not have any feedback loop, which results in 2 problems. Let's see what happens. First of all, that the torque oscillates with time. Because there is a finite number of poles, what happens is whenever the stator is in between 2 poles, there's a loss in torque, and it leads to a graph wherein it drops, then again comes to a threshold, then drops, then comes to a threshold, and so on and so forth. This changes in torque are not desirable, especially in electric motors which are used in heavy applications where heavy load is required, where torque is one of the main considerations while deciding motors. Another problem is that because of the switching is abrupt, and the fluctuations because of that results in the noise, which I'll show you. See, so this one is without FOC, and this one is with FOC. As you can clearly see that the noise is really different. The FOC, because the FOC has a feedback loop, the current is always in a, its slope is always monotonic rather than abrupt changes. These abrupt changes even lead to mechanical wear and tear in the motors, leading to a lower lifespan. Moving forward, what are the torque slip characteristics? So in a PMSM or an induction motor, this is a well-known formula, which is the torque would be directly proportional to the flux, the current, and the angle between the flux and the current. The current is dependent on a 3-phase AC signal. Normally, we can have a higher phase AC signal, but 3-phase is the normal, in normal use we use. So as you can see, the 3 things that are required is the magnitude of the rotor current, which is I, power factor of the rotor, which is the cos phi, and the flux which interacts with the rotor, which is the phi. So I is an input. The phi is changing continuously as and when the motor, as and when the stator and the rotor are moving. So what we require to get the maximum torque. As you can see this graph, this is the torque versus phase angle. The 0 degree, the 0 degree results in the highest torque, and the 90 degrees result in zero torque. So for a particular current, if we want to get the highest torque possible, then the ideal characteristic would be to have the current and the flux at the same angle. Now what happens is, naturally that doesn't happen, so we need to force it to happen. We need to have a clock with a high frequency, which would at particular instances of time create interrupts, which would then create a feedback loop, and the error of that feedback loop would be then fed again into the system, which would then reduce that error, and you will artificially try to align the current and the flux. How do we achieve this? So this is the original signal. If we assume this is the phasor diagram, and this is the angles. The A, B, and C are the input currents of the three phases of the motor. They vary in magnitude according to what the output of the current we require. Yeah, this is the animation. The neon blue, as you can see, is the final resultant net current output. Going on to this phasor diagram, as you can see, the IB, IC, IA, IB, and IC are net zero because of the Kirchhoff law. And from the three-phase signal, we can boil it down to a two-phase signal, which is called as the Clark transform. What happens is, we can just instead of using IC, we can use minus IC, which would just be minus IA minus IB. Then add the IA and the IB to get the net current vector. So the net current vector can be shown as a function of IA and IB, which is only two input functions rather than three. So eventually what we want to do is, rather than having three input functions, we reduce it to two to reduce the complexity. Why are we doing this? To get the net current vector, which would then be used to align with the flux of the motor, which would help us to have a higher torque on that particular current input. This is the Clark transformation, which is a simple matrix. The left hand side is the Clark transformation, the right hand side is the inverse Clark transformation. As you can see, what happens is, we are reducing the alpha, beta, and gamma of the, or reducing the A, B, and C of the input IA, IB, IC to just two, alpha and beta. C, which is stationary with respect to the motor housing. What happens is, as and when we require the current to have, the blue neon you can see is the current. The alpha and beta current values vary according to what we require the current. This method was invented by Edith Clark. She is a British national, a scientist. She is the first professional electrical engineer in the world. So this tells us the background of this. Coming forward to Park transform. So there's a guy named Robert Park, who thought, why not improvise this further? As you can see, let's assume a Hot Wheels. The car is moving in a circle. Rather than having a stationary point of view and seeing what the circle is, we can have a point of view of the car. We can have a axis which is in itself rotating, and then we'll just have DC signals to watch out for. So this is the Park transformation. This is the inverse Park transformation. I'll show you the animation. So ID and IQ here are moving synchronously with the motor, with the stator, which helps us to get a D and Q value, which is a DC values. This greatly reduces the complexity of our problem. Here Because of the nature of ID and IQ, we conventionally assign IQ to the torque value and ID with the flux value. This helps us in the FOC's main objective is to have a better control over the flux as well as the torque, rather than only the current input in the case of the PWM. So moving forward, so these are all the transformations. As you can see, the first one is the normal three-phase AC, then we transformed it to the Clark transform, and then finally we transform it to the Park transform. See, the simplicity of the Park transform is that it is just a DC signal. In case of PMSM motors, we reduce the ID to 0. Why do we do so? Because we do not want to change the flux, because the flux is directly, there is no slip in PMSM. So the flux is moving with the same frequency and the same phase as the stator current, stator field. Hence, keeping ID equal to 0 would not induce any extra phase, and we can simply change the IQ values according to what torque we need. Whereas in the case of induction motors, there is a certain slip, and to offset that slip, we have a particular ID value for each theta angle. This will help us in reducing the slip, the function of the slip in the flux. Moving forward, to field-oriented control, uh, going on, this helps us to understand how complex field-oriented control is. So as you can see, I'll use the laser. Yeah. As you can see, the Clark transform and the Park transforms are fed into the PI controller, which are then again converted to the three-phase AC signal, because at the end of it, we want to know what the three-phase AC signal has to be, because that would be our input. So we need to do the inverse Clark and Park transform. Here, one important thing to note is that we need to be aware of the mechanical to electrical position. We need to have a sensor which is either used as is either a Hall effect sensor, either an encoder, which helps us to understand the exact position of the flux. This position of the flux would then be converted into a sine cosine lookup and then would be fed into the error signal. This error signal would then help us to align the current and the flux values. The recent in the past decade or so, there have been an advent of sensorless FOCs, which is a clever way to simulate mathematically what the flux of the PMSM motor would be, rather than having a sensor, because having a sensor is costly and very logistically not very easy, because the motor is a moving mechanical part and having a sensor in them is difficult. Moving forward, the advantages of FOC is that we have a precise control over the torque and the flux. It has a better efficiency because we get the max torque for every current. It works better at low speeds. Why so? Because in the earlier example, as we saw, when there is a higher load on the shaft, there is an increase in harmonic oscillations. These harmonic oscillations lead to noise, which is absent in FOC, because even in case of a load, there is a continuous feedback at a high frequency, which reduces the uh, errors. As you can see, it also reduces the torque ripple. As I explained, the ripple, because of the finite number of volts, is reduced because there is a continuous feedback loop in place. Then I have written a code for the signal processing. I'll show it to you in a short while. I have done the Clark transformation, the Park transformation on a three-phase AC signal. Moving on, there's another code that I have written, which is to show that Clark and Park transform are invertible, which is very much required in all electrical systems, as we have done in class. Invertibility is a very important phenomenon, because we after all want to know the input that we want to give, which is a three-phase AC signal. The code shows how the input signal is converted to Clark, to converted to path, and then again retrieved using a inverse Clark and path transform. These after we have done that for a particular phase angle, I'll have to show that it is valid for every value of the phase, every value of the frequency, which is clearly shown here. This is our matrix for Clark transform. The determinant is root 3 by 2, which is not equal to 0, so invertibility is existent. Whereas in path transform, it is equal to 1. Here too, it is existent. The system in path transform is invertible, causal, because it does not depend on the past values. It is stable because it is used in electrical machines. It needs to be stable. It is linear, and it is time variant. Time variant because the theta, here you see the theta. Theta is a time varying function. The time varying function theta can be considered as the t in our case, and the t is result in the sign of t, as we know the trigonometric functions are time variant. Hence, and the Clark transform is time invariant because there is no theta in there. This is all.